All right, we're going to go ahead and start section 4.5, which is the exponential and logarithmic equations. So in section 4.3, we learned about logarithmic equations. In sections 4.1 and 4.2, we learned about exponential equations. In 4.4, we learned about some laws of logarithms. Now we're looking at equations that will contain exponential and logarithmic expressions within them. So how to solve an equation that has one of these types of expressions. So we learned about exponential and logarithmic functions. Now we'll learn how to solve equations containing them. The techniques that we learn that will help us solve applications using exponential or logarithmic functions. So solving these types of problems will help us in our last section, section 4.6, as well, so that we can use those kinds of applicational problems and still be able to solve for specific things within them. So as an example, one would be exponential growth, which is an example we see here with these bunnies. We see that 2 bunnies could turn into 5 bunnies, could then turn into a lot of bunnies. So that's exponential growth, which we'll go over in our next section. And so learning what we're learning today will help us solve the equations that we would need for something like exponential growth and things like that. So exponential equations, starting off, we say that since exponential functions are 1 to 1, which remember that means that one very specific x value goes to one specific y value and there's no sharing, we can use this property to solve some exponential equations. If we have something like a to the power of x is equal to a to the power of y, that really means that x equals y. So if you have 2 exponential expressions that have the exact same base but different exponents, those exponents are really equal. So that is one very simple way to kind of solve exponential equations. If it doesn't happen to be that simple, you can instead use guidelines to solve any exponential equation instead. The guidelines will be much more useful and you will have to use them much more than that first kind of fact there. But that first fact does help us with the guidelines. So anywho, we have the guidelines for solving exponential equations. Step 1, isolate the exponential expression on one side of the equation. So bring your exponential expression to one side. Step 2, you can take the logarithm of each side. And this could be any kind of logarithm, any logarithm that is easy. So it could be a logarithm of a very specific base based on the problem that you have, or it can just be the common logarithm and the natural logarithm in order to compute an answer. So you'll take the logarithm of each side, then you'll use the law of logarithms to bring down the exponent. So you do use that law of logarithms in order to bring the exponent, which will most likely be the variable, down to the front so it's no longer an exponent. And then you can actually solve for that variable. So that third law of logarithms is required in solving exponential equations. So it's very useful to have that one memorized, or at least very accessible. So those are going to be our guidelines for solving exponential equations. We've learned our one fact at the top here in addition to the guidelines, so we are now equipped with everything we need to solve exponential equations. So let's go ahead and try one out. So example 1, we're going to solve the exponential function 5 to the power of x is equal to 125. So let's go ahead and go on over to our notes so we can solve this one. All right, problem 1, 5 to the power of x is equal to 125. Before we just jump right into our guidelines, first we want to see, are we able to use that nice handy fact that we learned before? That fact being that if you have a to the power of x and it is set equal to a to the power of y, then that really means that x is equal to y. So if we take our problem, 5 to the power of x is equal to 125, we can think to ourselves, okay, well, is 125 going to be the value of 5 to some number? And you could test a couple numbers out in your calculators if you'd like, or if you already know the answer to this, excellent. 125 is the same thing as 5 to the power of 3. Go ahead and just highlight that real quick. So 125 is the same thing as 5 to the power of 3. So we could replace 125 with 5 to the power of 3. And now we have 5 to the power of x is equal to 5 to the power of 3. See that the base is the same in these cases, which tells us that x is really just 3. You could have also recognized that from just the very first step. 5 to what number is equal to 125? The answer would be x equals 3. So there we go. Problem 1 used that really nice, handy fact that we had on that last slide. Didn't necessarily have to use any guidelines in this case. It was pretty straightforward on solving for x. So let's go ahead and go on back to our lecture. All right, that was example 1. Let's go ahead and do example 2. We're going to solve the exponential function. We're going to find the exact solution and the approximate solution. So what this means is that the exact solution is the solution we get that is purely algebraic. You know, we solve the solution or we solve our problem using all the algebra and all the skills that we've learned throughout the section. And the approximate solution is the answer when we put it in the calculator. So the approximate solution is going to be like that decimal answer. It's the one you put in the calculator. The exact solution is your answer before you put it in the calculator. So that is the difference there. So we're going to do each one of these. And we have 3 to the power of x plus 2 is equal to 7. So this one we're going to have to actually use those guidelines because 7 is not going to be the result of 3 to any power that we know. We know that 3 to the power of 1 is 3, 3 to the power of 2 is 9, 7 is in between there. So we don't know that number x right off the bat. So we will have to use our guidelines for example 2. So let's go ahead and go on over to our notes to work this one out. All right, so for problem number 2, we have 3 to the power of x plus 2 is equal to 7. So we want to find what the value of x is going to be. And so we're going to use those guidelines that we had before for how to solve a problem like this. And the very first step is going to be to take a logarithm of both sides. We also want to make sure that we isolate the exponential term to one side, and that step is already done for us. It's 3 to the power of x plus 2 on one side alone, 7's on the other side. So step 1 is already done, which means that step 2 is to take a logarithm of both sides. So in this case, you have a couple options. You could take the common or the natural logarithm of both sides, or you could take log base 3 of both sides. If you took log base 3 of both sides, it would essentially cancel out the base of 3 and you would just have x plus 2 on one side. But then you would have to deal with log base 3 of 7. So that is one thing that you have to remember. But taking a common or a natural logarithm of both sides is going to make it for a kind of a cleaner answer. So that's what we're going to use. So let's go ahead. I always like to use the common logarithm, but once again, you can use the natural logarithm. The answer will be the same, the exact same way. It's the exact same process. It's just natural log instead of common logarithm. All right, so let's go ahead and use the common logarithm and take the log of both sides. So if we do that, we'll have log of 3 to the power of x plus 2 equal to the log of 7. So now that we have log of 3 to the power of x plus 2 equal to log of 7, we want to go ahead and use that third law of logarithms to take x plus 2 out of the exponent's place. So this is where that comes in. So this will use the third law of logarithms. And we're going to bring x plus 2 to the front of the logarithm. And now we'll be left with log of 3. So we have x plus 2 times log of 3 is equal to log of 7. And now we want to solve for x. We're going to go ahead, we're going to divide by log of 3 on both sides. It cancels on the left-hand side. we get x plus 2 is equal to log of 7 divided by log of 3. Solving for x, we can go ahead and subtract 2 from both sides. And we get x is equal to log of 7 divided by log of 3 minus 2. And that is our exact solution. So if this is our exact solution, you can have a couple different forms of the exact solution. The exact solution can be the form that we have here, or we can have the natural logs. So we can have x equals the natural log of 7 divided by the natural log of 3 minus 2. This is also an exact solution. Or if you took log base 3 of both sides instead of a common logarithm, this would have instead looked like log base 3 of 3 to the power of x plus 2 is equal to log base 3 of 7. You still are bringing that exponent out to the front using that third law of logarithms. So you'd have x plus 2 times log base 3 of 3. And this is equal to log base 3 of 7. The log of a base of the same number is always equal to 1. So like log base 3 of 3 is equal to 1. Log base 10 of 10 would be 1. Log base, 5 of 5 would be 1. So if the base and the value of the logarithm are the same, the answer is equal to 1. So we see that log base 3 of 3 really just kind of cancels itself out. It becomes 1 times x plus 2, and that's just x plus 2. So this would become x plus 2 is equal to log base 3 of 7. And solving for x, you get log base 3 of 7 minus 2. That is another exact solution. To have x is equal to log base 3 of 7 minus 2. So every one of these answers are all the exact solutions. You do not have to write all of them. You could just write one of them, but it would be considered correct. So these are exact. You would take one of these to be the exact solution. It is the answer that you get when you solve for x using your logarithms and your algebraic skills. The approximate solution is going to come from the exact solution. So you are going to use the exact solution and plug it into a calculator to find the approximate solution. So let's go ahead. We're going to grab our calculator. So remember our answers were log of 7 divided by log of 3 minus 2 will give us that exact solution. So we go ahead and we can type that in. Remember your logarithms that are being divided are one single term, so we want to make sure that we have parentheses around those. So we're going to parentheses log of 7 divided by log of 3, and then we'll end that division part there, minus 2, and we get our answer, negative 0.228756250.8, which we would most likely be rounding that number probably to about 5 decimal places, or however many a problem would tell you. For us, we're going to use the first 5, which means that this would be negative 0.22876 as our answer. So, all right. Now remember, we can do the same thing with the natural logarithm as well. We can have the natural logarithm of 7 divided by the natural logarithm of 3 minus 2, and we get the same answer. So either one of these would be the exact solution with the logarithms, and the approximate is the actual decimal answer. So that is the difference between an exact solution and the approximate solution. Now remember, we also said that log base 3 of 7 minus 2 can also be used as well as an exact solution, but remember, you would need to figure out how to do that in your own calculator to find that value. So a lot of calculators can do it. Not all calculators can do it. If you can figure out how your calculator can do it, then that is great. If not, this is how you would do it as well. So, all right, let's go ahead and go and put that back in our notes. So here we are. We said our approximate solution was negative 0.22876. So this was our approximate solution that corresponded to our exact solutions from above. So, all right, that wraps up problem 2. So let's go ahead and go on back to our lecture. All right, so that was example 2. Moving on to logarithmic equations. So we were just looking at exponential equations, so how to solve an equation that had an exponential expression in it. Now we're going to do the same thing with logarithmic expressions. So since logarithmic expressions are also one-to-one, we can use the same type of property that we had before to solve some logarithmic equations. Log of base a of x, if it's equal to log base a of y, then that means that x and y are equal. So in that case, this is kind of the same type of like easy little quick way, if it works out, to find a solution of a logarithm. But most problems won't be quite as easy. So instead, we use the guidelines. So you can use the guidelines to solve any logarithmic equation. But as a quick note, some functions actually have to be graphed in order to find solutions. Remember, solutions are x-intercepts. So sometimes you have to graph a function in order to find that x-intercept as the solution. There are some, I think just maybe 1-2 problems on your homework where it has to be graphed in order to find those values. Yet you will not be able to find them using our guidelines here. You have to graph it. So you would have to graph a function in order to find its x-intercepts. All right, so just putting that out there. But anywho, guidelines for solving logarithmic equations. Step 1, isolate the logarithmic term on one side of the equation. You may need to first combine any logarithmic terms if they're not in one single term. You have to have it in one single logarithmic term, meaning that you want to combine any of your logarithms into one. So that's using those skills that we learned in our last section, section 4.4, in order to combine a logarithmic expression into one logarithmic term. So you need to isolate and combine your logarithmic terms to one side. Step 2, write your equation in exponential form. So take your logarithm and rewrite it in exponential form. We said that logarithms are really just rewritten exponents. So you want to put it back into its exponential form. This is also the same thing as raising the base to each side of the equation. So you would find the base and raise each side of your equation into an exponent of a logarithm. You'll see this put into place or put into action a little bit more in our next example. And then lastly, part 3, solve the variable. So you can solve the variable that you want to solve for. So, all right, those are the instructions on our guidelines for how we would find logarithmic equations or how we would solve them, equations that involve logarithmic expressions. So, all right, we're going to go ahead and do example 3. We're going to solve the logarithmic function. 4 plus 3 times log of 2x is equal to 16. So, all right, we're going to go on over to our notes to work this out. All right, so example 3, we have 4 plus 3 times log of 2x is equal to 16. So on our guidelines, we said the first step was to isolate the logarithmic expression as much as possible. So we want the logarithm without any coefficients and without any numbers being added or subtracted. So we've got 4 plus our logarithmic term. So we can go ahead, we can get rid of that 4. So we can subtract 4 on both sides. Cancels out on this side. We end up with 3 log of 2x is equal to 12. So at this point, we have two options. We have 3 times log of 2x, and it's equal to 12. You could take the 3, which is a coefficient of the logarithm, and use the third law of logarithms to put that 3 into the exponent on x. This would create log of 2x cubed equal to 12. You have that option, or you could divide each side by 3. 12 divided by 3 is just 4, so our answer would come out pretty nice. But if it was in the case that you could not divide the number on the opposite side by, the coefficient, maybe you'd rather put it into an exponent and do that instead. So you have some options on kind of how you want to go about a problem like this. So since it's easy to just divide 12 by 3, we can just get rid of the 3 by dividing on each side. But if it doesn't quite work out this way, you can always make that 3 into an exponent instead. So you can always keep that in mind. So, all right, we're going to divide each side by 3. The 3's cancel out on the left-hand side. We get log of 2x is equal to 4. So log of 2x is equal to 4. Now, in order to solve the logarithmic expression, we said that we could rewrite our logarithm in the form of an exponent. So let's go ahead and remember what that looks like. We say that for an exponent, log base, let's say a of y is equal to x, and in exponential form, this would be a to the power of x is equal to y. So in our case, we have log of 2x is equal to 4. So we can go ahead and kind of identify those terms. So in our case, we have that 2x is really that value of y. Then we have 4 is the exponent, x. And we have log with no base. Remember that log of no base means base 10. And this right here means a is 10. So we already have in the form of log base 10 of 2x is equal to 4. And we can go ahead, we know what a, x, and y are, so we can go ahead and we can rewrite it in its exponential form instead. This would turn log base 10 of 2x is equal to 4 into 10 to the power of 4 is equal to 2x. And now we can solve for x. So we kind of see how that happened. We just rearranged, kind of flipped everything around a little bit. And now to solve for this problem here, we could solve for x. We say 10 to the power of 4. 10 to the power of 4 is going to be 10,000. So we would have 2x is equal to 10,000. Divide by x. Or divide by 2 to get x. There we go. We get that x is 5,000, not 10,000. And there we have it. X is 5,000. So what we were talking about there was that we took our logarithm and we just rewrote it into its exponential form, because logarithms and exponents are really the same thing. We're just rewriting it. So we take our logarithm, put it into an exponential form, and then we solve for x. And there we go, x is 5,000. Another way that you could go about doing this is, it's really essentially the same thing. It's just kind of worded slightly different. So, ooh, wrong one. There we go. So, in this case, what you could do is identify the base of the logarithm. This is the common log, so it's base 10. So you would take that number, 10, and you would make each side of this expression an exponent of 10. So this would turn into 10 to the power of log of 2x, which is equal to 10 to the power of 4. So that is another way that you can kind of go about this. Identify the base of the logarithm and take each side of the equation and turn them into exponents of that base. So we said it was base 10, so this turned into 10 to the power of log base 10 of 2x is equal to 10 to the power of 4, because that was what was on the other side of the equation. Then you could simplify any number, and this was one of our identities, any number of some base to the power of log of the same base cancels itself out. So essentially, these will cancel each other out. All you're left with is that 2x, and 10 to the power of 4 is 10,000. Divided by 2 on each side, and x is 5,000. Same answer. So these are two different ways that you could go about it. It is essentially doing the same thing. It's just two slightly different ways of actually writing it. So you could either rearrange your logarithm to be in its exponential form, or you could identify the base of the logarithm and turn each side of those equations into exponents of that base. That will inherently cancel out the logarithm on that side that had the logarithm. You would be left with whatever you were taking the logarithm of, which almost always would have that variable. The other side simplifies, and you solve for that variable. So it is a couple extra steps if you are going to kind of take each side of the equation and turn them into exponents of that base. But it does work, and you don't necessarily have to memorize the exponential kind of formula and how it relates to a logarithm, although it's very important to remember. So keep that in mind. You do have two options there. You could pick kind of either format to go with in order to solve a logarithmic equation. So, all right, that finishes up example 3 here. So let's go ahead and go back to our lecture. All right, so that was example 3. Moving on, we're kind of revisiting compound interest. So recall the formulas for interest. We had A was equal to P times 1 plus R, the simple interest rate for just 1 year. A of t is equal to P times 1 plus R over n to the power of n times t. This is interest compounded n times per year. Then we have A of t is equal to P times e to the power of RT, where interest is compounded continuously, so every moment of every day of every year. So those are the formulas for part A, or part A. For the first one, we have the simple interest formula. That's just for one single year. So if you just want the interest for 1 year, that is how you would do it for simple interest. If you wanted simple interest for a couple of years, you would just take that times however many years you had. Then for the second one, A of t is equal to the principal, the original amount, times 1 plus the interest rate, divided by n, the number of times that you compound interest per year, to the power of n times t, which is the number of years. And then we have A of t was that principal times the exponential number e to the power of the interest rate times t, the number of years. So these were the different formulas that we had for interest that we've kind of learned over chapter 4. Now we can use logarithms to determine the time it takes for the principal to increase to a given amount. So previously, when we were using these formulas, we were really just mostly solving A of t, or maybe even the principal as well, the original amount to get to a specific amount, or you invest a specific amount to get to how much money. But now, since we know how to solve equations that have logarithms, we can now also solve for time. So the time it would take for the principal to increase to a given amount. So we're going to go ahead and try this out with example 4. So a sum of $5,000 is invested at an interest rate of 5% per year. We want to find the time required for the money to double if the interest is compounded continuously. So we're using the continuously compounded formula, the principal times the number e to the power of r times t. So we're using the compounded continuous formula. We want the money to be doubled, and we're starting with 5,000, which means that we want to know when is it going to reach 10,000. The principal was $5,000, and the interest rate was 5% per year. And we're finding time, t. So let's go ahead and go to our notes so we can go ahead and solve this. All right, so example 4, we have that the principal is $5,000. The amount after however much time this is going to take us should be twice the principal, so 2 times p. P, or our principal, was 5,000 times 2 is 10,000. So A of t should be 10,000. And the rate was 5%, which is 0.05. So let's go ahead and put this into our continuously compounded interest formula, which is A of t is equal to the principal times e to the power of the interest rate times time. Now remember, we're finding time. So we're going to plug all our values in. A of t was 10,000. Principal is 5,000 times the number e to the power of the rate, 0.05, times t for time. And t is what we're solving for. So we can go ahead and we can start out our problem. We have our exponential expression e to the power of 0.05t that we want to be isolated by itself. So we can get rid of that 5,000. So let's go ahead and divide each side by 5,000. Ooh, I wrote 5,200. So 5,000 cancels out on the right-hand side there. I'm going to switch the sides just because I personally like the variable to be on the left-hand side, but you could leave it like this if you'd like. This turns into e to the power of 0.05t is equal to 2. So we've got e to the power of, 0.05t. This is equal to 2. We want to solve for t. And in this case, we have the number e as the base. So we could very easily take the natural log of both sides, and we could cancel out that e. Now you could take a logarithm of any base. It doesn't necessarily matter. You could take log base 10 of both sides if you'd like, or a log of any base. But remember, e and the natural log are inverses. So if we take the natural log of both sides, it will automatically cancel out the e and just make everything that much easier for us. So we're going to take the natural log of both sides. So this will turn into the natural log of e to the power of 0.05t equal to the natural log of 2. Now what happens here is that we use the third law of logarithms to take 0.05t and bring it out to the front of the logarithm. This becomes 0.05t times the natural log of e which is equal to the natural log of 2. The natural log of e is just equal to 1. So since it's equal to 1, it really doesn't affect 0.05t at all. So we get 0.05t is equal to the natural log of 2. We want to solve for t. We'll divide each side by 0.05. Cancels out on the left-hand side. And we're left with t is equal to the natural log of 2 divided by 0.05. So t is equal to the natural log of 2 divided by 0.05. We want to find how long is this really? And remember, t is always in years. So whatever your answer is, it's in years. So natural log of 2 divided by 0.05. We can go ahead, we can plug that into our calculators fairly easily as long as we know how to use our calculators. And if you've done it already at this point, you would find that the answer, rounded to 2 decimal places, would be 13.86 years. So it would take 13.86 years for an investment of $5,000 to turn into $10,000 at an interest rate of 5% being continuously compounded. That's a pretty long time. Maybe not the best investment. Maybe try to get a higher interest rate. But all right, so there was our answer, 13.86 years, and that is how we would solve a function like this. Now, remember, if it comes to a problem where you don't necessarily have continuously compounded interest, meaning that you don't have e, you would have to take the a logarithm of a base that was probably some pretty ugly number, because it would be 1 plus the rate divided by n, where n is the number of times you compound per year. Maybe the number doesn't come out all that great. You would have to use the change of base formula, or if you had a calculator that could calculate the logarithm of any base, you could use that as well. So it could become a little bit more difficult if you try to solve a problem in that way, if it's not continuously compounded interest. So, all right, let's go ahead and go back on over to our notes, or to our lecture. All right, so that was example 4, and that wraps up section 4.5. So in summary, in section 4.5, we learned about exponential equations, logarithmic equations, and compound interest. This is really how to solve equations that use exponents and logarithmic expressions within them, so we can now solve basically any type of equation. This sets us up for success in our last section, section 4.6. All right, that finishes up section 4.5, and I'll see you again in section 4.6.